It's
It's too difficult.
okay. Maybe I can explain. Okay. Yeah. Now the other definition is the other notation is the geometric index. If we have a two solid torus n prime and n prime is the subset of the interior of n. The geometric index n prime in n is the minimum number of the points in the intersection of the core of n prime with the meridian disk of n. Okay, so maybe here I can explain. Here this okay. So maybe I can explain this, that give an example to explain the definition. Let's go back to the picture. No. Yeah. Here, maybe we can say we can find a disk bound the blue curve. The disk will intersect the red curve at the 2 points. So from this picture, we know in this picture the geometric index is equal to 2. Okay. And yeah, so we know for example, in the Wang manifold, the geometric index nk in nk plus 1 is equal to 2 for each k. This is important for the proof. Yeah. Okay. I can make some remark. In the definition, we just count the points in the intersection. We don't care about the orientation. If we consider orientation, we will get the definition will become the intersection member. Okay, maybe next. Yeah. I would like to introduce a class of 3 manifolds. The genus 1 3 manifolds. A genus 1 3 manifolds is a increasing union of solid torus nk, such that for each k, nk is a subset of the interior of nk plus 1, and the geometric index of nk in nk plus 1 is not equal to 0. From above the statement, we know the geometric index nk in nk plus 1 is equal to 2 in the Wang manifold. So we know Wang manifold is genus 1 3 manifolds. Okay. Actually, the Macmillan showed that a contractible genus 1 3 manifolds is not homeomorphic to R3. The proof is easy and use the geometric index. In particular, the R3 is not genus 1, genus 2. Okay, because R3 is increasing union of 3 balls. 3 ball is a genus 0 kind of body. Okay. Yeah, we use a minimal surface to show that no contractible genus 1 3 manifolds has a complete metric with a non-negative scalar curve. Yeah, in particular, the Wang manifold does not have a complete metric with a non-negative scalar curvature. Okay, in the following, we were just talking about the proof for the Wang manifold and for the positive scalar curvature metric, because the proof for genus 1 case is same as the proof for Wang manifolds. Yeah, actually, we can use the Constant's result to generalize the result for the positive scalar curvature to the non-negative scalar curvature case. Okay, we're talking about how to prove this result. This result for Wang manifolds. We argued by contradiction. So we suppose Wang manifolds has a complete metric with a positive scalar curvature. So we know Wang manifold is increasing union of solid torus, and the nk minus 1 is embedded in nk in the same way as the T1 located in T2. Please go back to the construction. Here, the solid torus. Okay, the solid torus is nk, and the red curve is nk minus 1, and the blue curve is gamma k. Gamma k is a meridian curve of nk. Okay, so we choose a meridian curve gamma k of nk for each k. Roughly speaking, each gamma k bounds are embedded stable minimal disk in nk. Okay, now we consider the simple case when dk converges to a complete collected stable minimal surface in white-hot manifolds with a finite multiplicity. Because the scalar curvature is positive, Shunyao result tells us L is homeomorphic to R2. Okay. Furthermore, we show that the integral of the scalar curvature of the white-hot manifolds along L is unbounded by 2 pi. This equality is so-called extrinsic convention equality. The proof for this equality, we need the positive scalar curvature condition. Okay, in general, the dk subconvenes to a lamination in C0 alpha topology. The lamination is a closed set in the white-hot manifolds. It's disjoint union of some embedded surface. It may have infinity many components. Each component is an embedded stable minimal surface. Okay. Because the scalar curvature is positive, we know each stable minimal surface is a plane. That means each stable minimal surface is a diffeomorphic to R2. Okay, now we explain how to get a contradiction. The first one, from the topological part, we know that each intersection of the dk with the n1 has at least 2 power k minus 1 components intersecting n0 for each k. Okay, maybe I can explain it. Construction. Oh, yes. From this picture, we can say the solid torus is nk, and the red curve is nk minus 1. Okay, we can. The dk is a disk bound this blue curve. So we know this disk intersects the red curve at 2 points. Yeah. So roughly speaking, we know the dk intersect nk minus 1 has 2 components. Each component is a meridian curve, meridian disk of nk minus 1. So each component intersect nk minus 2 has 2 components. Each component is the meridian disk of nk minus 1. So that we know the dk intersect nk minus 2 has 2 power 2 components. Each component is a meridian disk of nk minus 2. So we can repeat the arguments. We know the statement. Okay, because L is limit of dk, the intersection of L and the n1 has infinity many components intersecting n0. Okay, from the Mix-Yau's work, we can find a positive constant C1. This constant depends on the metric. Okay, such that the area of each component is not less than C1. So because we have the intersection have the infinity many components. That means the intersection of the L and the N1 has an infinity area. Okay. From the geometric part, we know the integral of the scalar curvature of the white-height manifolds along the L is outbounded by 2 pi. So we can find a constant C2. The scalar curvature is bounded below by C2. From this equality, we know the area of the intersection of L and the N1 is finite. So we get a contradiction. Okay, it's okay for anyone has some question about this proof? No? Okay. So next. Okay, in the following, I would like talking about the general theory for contractible 3 manifold and the related rigidity results. Okay. Okay. First, I would like give the for and the positive answer to about question. We show that a complete contractible 3 manifolds with a non-negative scalar curvature is homeomorphic to R3. Okay. Okay, I would like to recall some classical results about the topological structure of the contractible 3 manifolds. Macmillan and Perelman show that a contractible 3 manifold can be written as the increasing union of handbodies. For example, the R3 is the increasing union of 3 balls. 3 ball is a genus 0 handbody. White-height manifolds is the increasing union of the solid torus. Solid torus is genus 1 handbodies. Okay. The topological structure at the infinity of the contractible 3 manifolds is characterized by the symplectic correctness at infinity. Okay. A manifold is simply collected for a compact set K. If there is a compact set K prime in M contain K, so the induced map from the fundamental group of M delete M prime M delete K prime map to fundamental group of M delete K is trivial. That means any closed curve outside K prime is contractible in M delete K. So a manifold is simply collected at infinity if M is simply collected for any compact subset of M. Okay, for example, we know the Rn is simply collected at infinity where n greater than 2. R2 is not simply collected at infinity because we delete a disk on R2, the fundamental group is non-trivial. Oh, okay. The Sterling and the Perelman's results implies that a contractible 3 manifolds is homeomorphic to R3 if and only if the manifold is simply collected at infinity. Okay. When we consider the topological structure of the contractible 3 manifolds, so we should study the topology at the infinity of the contractible 3 manifolds. So, but here maybe we know the topological structure is still complicated at infinity. So now we just consider the minimal surface behavior at infinity. Okay, let the L be a complete properly embedded minimal surface, minimal plane. A plane means this surface is diffeomorphism to R2. Okay, the plane is trivial for a compact set if there's a compact set K prime contains K, such that the induced map of the fundamental group L delete K map to fundamental group M delete K is trivial. That means any closed curve on on L outside K prime is contractible in M delete K. Okay, the L is trivial at infinity if L is trivial for any compact subset of M. Okay, let me make a remark. There is a long property embedded minimal plane in a contractible three manifolds. Actually, in my proof, we will use the L do a surgery. Actually, we will cut the three manifold along the L. So we need the L is properly embedded. Okay, let me make some remark. Let's M be a complete contractible Riemannian manifold and L a properly embedded minimal plane. If L is not trivial for some compact set K, then M is not simply collected for K, and L will intersect K. If L is not trivial at infinity, then M is not simply collected at infinity. Okay. Furthermore, we have that let M is and L be as above. Assume that L cuts M into the two components, M1 and M2. Okay. If L is not trivial for some compact set K, then the closure MI is not simply collected for K intersect the closure of MI for I equal to 1 or 2. If L is not trivial at infinity, then closure of MI is not trivial, so not simply collected at infinity for I equal to 1 and or 2. Okay, roughly speaking, if a contractible Riemannian three manifolds it's not simply collected for a compact set K, there is a stable minimal plane L in the interior of M, which is not trivial for K. I will explain how to find such a minimal plane later. Okay. The triviality at infinity has a delicate has many collections with the minimal surface, the minimal plane. So this collection is so this collection is suggested by the following results. Okay, let M be a complete contractible three manifolds with positive scalar curvature. Then each embedded stable minimal plane is trivial at infinity. Okay, actually we can it's okay. Okay, now we can use this result to get a proof for the main result too. We argued by contradiction. Suppose a complete contractible three manifolds M with a positive scalar curvature is not homeomorphic to R3. M can be written as the increasing union of the hand body NK. The M is because M is not homeomorphic to R3, M is not simply collected at infinity. That means the M is not simply collected for some compact sets. We may assume M is not simply collected for M0. Okay, so we can find for each K. So we have that for each K there is a closed curve gamma K on the boundary of the NK such that gamma K is not contractible in M delete N0, and the gamma is non-contractible is contractible in N. Okay, the existence of the gamma K comes from the fact M is not simply collected for N0. Okay, now we construct the minimal surface. If the N and the metric G restrict to NK has a mean convex boundary. Mean convex boundary means the mean curvature of the boundary is non-negative. Okay, there we can find embedded stable minimal disk dk in NK with the boundary gamma K. This result due to mix Yao. Okay, if not, we can find the new metric GK on NK such that the GK is equal to original metric on NK minus 1. And the NK has a mean convex boundary for new metric. Okay, so we use the mix work again to find our embedded disk dk in NK with the boundary gamma k. Okay, the dk is the stable minimum for the gk, not for original metric. So we consider the intersection of the dk and the nk minus 1. This intersection is stable for original metric for G, and the dk intersect N0. Okay. Okay. In the following, we only consider the case when dk converges to a stable minimal plane L with a finite multiplicity. Because the scalar curvature is positive, we have that L is trivial for N0. Go back to the thing for the tree. Yeah. No. Yeah, here. Actually, we prove that in a complete contractible 3-manifold with positive scalar curvature, each embedded stable minimal plane is trivial at infinity. So each plane is a stable minimal plane is also trivial for N0. Okay, because the each gamma k is non-contractible in M delete N0, so L is not true for N0, we get a contradiction. Generally, the limit of the dk is a lamination. That means the limit is a disjoint union of some the embedded surface. Each leaf of the limit is a complete stable minimal plane, because the gamma k is here is a typo. The gamma k is non-contractible in M delete N0. So we know the one of the leaf of the limits is non-trivial for N0. So okay, to get from the positive scalar curvature to non-negative scalar curvature, we use the following Castle results. This result is due to the Castle. Castle shows that a complete long-reach flat metric with a non-negative scalar curvature can be deformed to be a complete metric with positive scalar curvature. So we use this result that can generalize the result for positive scalar curvature case, for positive scalar curvature metric to non-negative scalar curvature case. Okay, that's it.
Okay. We have time for questions. Yeah, we have plenty of time.
Okay, maybe I can talk more about how to get maybe next.
There's something.
Next. Okay. Yeah, actually, we can talk about how to get these results. Okay, so okay, first let me make some remark. If M is a complete contractible 3-manifold and L is a complete embedded stable minimal surface, this surface is connected, just has one component. Okay, L is diffeomorphic it's homeomorphic to R2. This is Shongyang's work. Yeah, and the integral of the scalar curvature of the M along the L is upbound by 2 pi. Okay, so we know L is properly embedded. This is important because in my proof, we will use the L cuts the L cut M. So okay. Okay, but we argued by contradiction. We suppose, we suppose that there is a stable minimal plane in M, which is not trivial for some compact set K. Yeah. So step one, we consider the set. This set elements is a complete stable minimal plane in M, which is not trivial for K. We have that this set is non-empty, and each element in this set intersects K. Okay, so we define the distance from the D, from one point P to the L. L is one element in this set. So we know this distance D is finite because each L intersect K. K is a compact set. Okay. So step two, we can find embedded stable minimal plane L in the set with the distance this from P to L equal to D. Okay, because we can consider the maximal sequence. Okay, and we consider the limits of this sequence. The limit is the required target, the required plane. Okay. Step three, we use the definition. We can show that there is no embedded stable minimal plane in M prime, which is non-trivial for K, where M prime is the component M deletes L, with P is not in M prime. But please say picture. If L prime is non-trivial for K, we can get a contradiction because from this picture we know the distance from P to L prime is greater than the distance from P to L. Yeah, but from the L prime is non-trivial for K, so L is belong to the set C. Yeah, so we get a contradiction with the definition of D. Okay, but the L is not trivial for K. That means the closure of M prime is not simply collected for K intersect closure of M prime. Roughly speaking, yeah, there is a stable minimal plane in interior of the M prime, which is not true for K. So we get a contradiction. We finish in the results.
Okay, so this time this is the end of the file. Okay.
Yeah, yes.
So thank you, Jan. Do you have question? No.
No.
So thank you again for the talk.
Thank you.
And we'll resume at 14? 2 p.m. 2 p.m. Paris time.
Centrale européenne.
Quoi?
La centrale européenne.
Ah bah, on est pas au centre de l'Europe.
Ah bon?